Hello everyone. Uh, we're going to demonstrate a sum. It asks us. Well, let me write down the sum. Oops. Show that the group G equals 0, 1, 2, 3 with the binary operation plus modulo 4. This group and the group G prime, which is equal to 1, minus 1, imaginary, and I and minus I, and the binary operation dot, which is a multiplication. These two are isomorphic. So what is isomorphism? Isomorphism is basically one, a homomorphism, and two, there's a one-to-one, one-to-one, and onto mapping. So we have to prove these two basically. Let's start with the first one. So we prove it's a homomorphism, or I think it's more convenient to start with the second one. Why you'll eventually get to know. Let's start with the second one. So we have to find a mapping. We have to find a mapping, say xi, from G to the group G prime, which is 1-to-1, which is 1-to-1, and which is onto. Now, how do we do the mapping? So what is a mapping basically? Mapping is, say this is G and this is G prime, and here are the elements of G. 0, 1, 2, 3, and here are the elements of G prime, 1, minus 1, I, and minus I. There has to be a mapping from an element of G to an element of G prime such that the order of the element being mapped and the order of the element which it is mapped to should be the same. So the order of the element being mapped in G should have the same order as the order of the element being mapped to in G prime. So how do we figure that out? We figure that out using the chart we create to find the order. So we have the elements of G and we have the order of the elements of G. So all the elements of G are 0, 1, 2, and 3, and we have to find the orders. So how do you find the orders? This is how we find the orders. So 0 is the identity element with respect to G with respect to the operation plus modulo 4. So the order of the identity element is always 1. What is the order of 1? What is the order of 1? So 1 plus modulo 4, 1 gives us 2, plus modulo 4, 1 gives us 3, plus modulo 4, 1 gives us 4, which is 0. So 0 is the identity element, so the order of 1 is 4. We come to 2. 2 plus modulo 4 2 gives us 0, which is the identity element, so the order of 2 is 2. And 3 plus modulo 4 3 gives us 6 plus 6 is equal to 2 plus modulo 4 3 gives us 1 plus modulo 4 3 gives us 0, which is the identity element, and therefore the order of 3 is 4. This is for G. Now let's come to the set G prime, or rather the group G prime. So the elements are 1, -1, I, and -I. Now 1 is the identity element. So order of 1 is 1. -1 into -1 is 1, so the order is 2. Minus a I into I is equal to -1. Again, I into I is another -1, which gives us, so this is -1, and this would give us another -1, -1, and that would give us 1, so the order is 4. And last but not the least, -I, this gives us -1, -I, this gives us another -1, and the order, and this gives us the result 1, so the order again is 4. Now if we compare these two tables, we will see that the order of 0 is equal to the order of 1, and the order of 1 is equal to the order of I, the order of 2 is equal to the order of -1, and the order of 3 is equal to the order of -I. So we can think of a mapping say phi from G to G prime such that phi of 0 is 1, phi of 1 is I, phi of 2 is -1, and phi of 3 is -I. Right? We prove, now this is clearly 1 to 1 and onto, because every element maps to a definitely single element of, every element of G maps to a single element of G prime, and every element of G prime is an image of exactly one element of G. So this is 1 to 1 and onto, and hence it is a bijection. So we have proved it is a bijection. Phi is a bijection, that is. What is left to be proved is phi is a homomorphism. So let us define the operation plus and dot on phi as follows. So phi 0, so phi a into phi b, phi a dot phi b would be phi of a modulo 4 addition b. Now let us see if this creates a homomorphism. Or let us do it differently. Instead of writing this, what we write is, we prove that this holds. In other words, phi is a homomorphism. This is to be proved, okay? And the manner in which we prove it is that this holds for all A, B belongs to G. So let's see, phi of 0 into phi of 1 is phi of 0 plus modulo 4 1, which is phi of 1. And what is phi of 1? It is I. And what do we have on the left hand side? Oops, let's not write it like this. So what you have on the left hand side is 1 into LH is equal to 1 into I, which is I, and RHS is equal to I. So this is fine. Next we have 0 dot phi 0 dot phi 2, and that gives us phi 0 plus modulo 4 2, which is gives us phi 2. How much is phi 2? Phi 2 is minus 1. So LHS is 1 into minus 1, which is minus 1. RHS is minus 1. So clearly this holds. Phi 0 into phi 3 would likely will give us phi 3 is minus I. Oops. Phi 3 is minus I, so it gives us minus I, and phi 0 plus modulo 4 3 would give us phi 3, which would again be minus I. Okay, last but not the least, no, we come to phi 1 dot of phi 2, which gives us phi 1 plus modulo 4 2, which is phi 3. LHS is, how much is phi 1? Phi 1 is 1, is I. Phi 2 is 1, so it gets I. Oops. Phi 2 is minus 1, so we get minus I. And RHS is equal to phi 3, which is minus I. Again, phi 1, phi 3 gives us phi 1 plus modulo 4 3, which is phi 0, which is 1. And here you can clearly see 1, phi 1 is I, and phi 3 is minus I. If you combine the two, you get 1 as well. So this holds as well. And the last but not the least, we have phi 2 dot phi 3, which gives us phi 2 plus modulo 4 3, which gives us phi 1, and phi 1 is I. And here we get minus 1 into minus I, which again gives us I. So clearly phi is a homomorphism, which is also 1-to-1 and onto, hence phi is an isomorphism. Hence proved. Thank you.